Hello and a warm welcome back. Today on the bench once again is the 2C34 push-pull class AB2 amplifier. As you may notice, I've rebuilt it once again. So spin you around to the other side. I ripped all that side out, so that was built once. This side was this is the third time I've rebuilt it. I'm going to try and put some pictures up now to try and show you what I was trying to get at, to try and make it all neat and reasonably compact without wires all over the place. I mean, yes, we've got some wires here, but they're just temporary. So you see by those photos that I've just shown, that was the sort of standard of work I was trying to achieve. So the reason I didn't like the iterations that I built of this before was because there was too many wires and then I couldn't get in to test the various test points. This is a lot neater. So essentially what I've done, I've put the constant current sources for the cathode followers on this board here. Change the cathode follower circuit a little bit, it's a little bit busier. Same with this one, put this one over here, and that's driving the long tail pair. That's a current source for the long tail pair. And as you can see, it's a, I can get in with me, to check the voltages. Right, what I'm going to do now is power it up, and we've still got a problem. So as you can see there, that's the output of the amplifier, and it's looking really nice sine wave. The original sort of spurious high frequency oscillation on the bottom part of the waveform, that's gone. I'm not quite sure whether that's due to the different construction or the fact that I've got a couple of RF chokes there on the anodes. And at the moment that's with an output of 2.6 volts RMS. And the distortion is rather respectable at 0.4%. Right, what I'm going to do now is increase the input. Just adjust that. Right, still not looking too bad. Although, right, of course you're going to do that, aren't you? So as you can see, there is some slight distortion at the bottom there, and that's at 5 volts RMS, which is, what's the distortion? Right, the distortion's sort of gone up to 2.6%. That's quite an increase. That was just a doubling of the input voltage from 50 millivolts RMS in to 100 millivolts RMS in. Right, I'm going to increase the level some more now, and you'll see a lot more distortion. Amplitude 0.2 V. Let's see if we can make that. Of course it's not going to bloody let me, is it? Can we? Right, sod about, aren't you? Right. So as you can see there, look, we're getting some sort of distortion at the top. That's and we've got an output of about 9 volts RMS, and the distortion is 5%. So we've got some distortion there. So now what I'm going to do, this is coming off the dummy load, this is what we would hear at the speaker as it were, and I'm going to probe through the amplifier different points. So this is the waveform on one anode. and as you can see we have got this distortion. Right, let me just, right, we haven't got a bloody ground thing, have we, on this? Right, we'll just have to wing it. This is on another anode, same problem. So that's off one of the two C34s, and the second one was off the other two C34. Right, well, let's go and have a look at the waveform on the grid of 1, 2, C34. As you can see, there is a little bit of distortion there, but it's not too bad. So I'm not quite sure why this is. Where are we? 8, what was that, 9 volts. Let me just do a 19.0 special. Right, so that was the 9 volt output, 9 volt RMS output equates to about 9 watts. We should be getting double that. So what's going off? So you can see, look, there's my probe from my scope onto the grids of one of the two C34s. When you drive in class AB2, what essentially is happening, that those two grids there that are joined together, they are basically conducting, the grids are conducting, and there's current flowing into the grid. So there's some sort of bit like a diode action. Instead of it being a triode, it's starting to turn into a diode. And so what you need, that's why we've got the cathode followers, what we need is like lots of current going in there to obviously, you know, drive the grids, and also it must have a low output impedance, which these cathode followers do. Now at the moment, these, I've got a 6H8C in there, and each one of those triodes is running at 8 milliamps, which from my calculations is sufficient. So let's just try turning the frequency up. Frequency 20 kilohertz. See, at 20 kilohertz we still got that, we still got this nonsense. Let's actually have a look on the, there we go. Right, this is the output. Right, so as you can see, we've got gross distortion there. Distortion is at 12%, so obviously that is going to sound really distorted. I'm going to change the current of the constant current sinks, make it higher, make it lower, see whether that improves things. Well, this I don't know what the hell's going on. Earlier on I was taking a reading from the grid of 1, 2, 3, 4, 4 and basically setting the current that, you know, the constant current sink. And when I was doing that, I slipped and there was a spark, and then everything, you know, seemed to be okay. And then later on, these two resistors here totally went open the circuit, and then later on still these two resistors started smoking. They were still alright. And then so I was basically going through a process of gently winding up the voltage on the variac, and then it started blowing the main HT fuse. So I was sort of trying to nurse it and just trying to take a few readings just to find out what the hell was going off. And then this resistor here, which is just a sense resistor, which goes from the collector of a MGE 340, which is part of the constant current sink. As you can see, that's completely burnt out. So yeah, big sparks, big bang, and it's killed the transistor, the bottom one there, the MGE 340. So again, it's doing weird shit, so I don't know what the hell's going off. And it wasn't oscillating at high frequency. I mean, I've got the input of the amplifier shorted. I've got, you know, the grid shorted to ground, so it wasn't oscillating. I don't know what the hell's going off. So I'm going to take some valves out and test the valves and take it from there, and obviously fix the constant current source and replace the what do you call it, the resistor here. Bloody hell, this amplifier. Here we are sometime later, fixed all the blowy upness that I'd created. Essentially what had happened was that 1, 2, 3, 4 got killed, I suspect, by me shorting the minus 80 volt rail to the heater, maybe, and just killing the heater. Anyway, it's got no emission, so I've got another 2C34 in there. Here we are, we've got a 1 kilohertz sine wave on the scope. As you can see, we've got some silly bloody business here. Don't look too bad there. I mean, it's not perfect, but that's not good. So what is what is doing that? So I'm gonna, at the moment, this is feeding, this here is from my 8 ohm dummy load. Take that off there. Sticky normal scope probe in there, set to 1 times. There's the amplifier. What could it be then? So let's suspect the output valves. But first, what I'm going to do, instead of probing the anodes, which I could do over here, I'm going to look at the grid. Let's go back to the scope, adjust our oscilloscope. Now that looks alright to me, that looks a decent sine wave, and my analyzer is saying we've got a 23 volt RMS sine wave with 2.8% distortion. Not too bad. I mean, yeah, not brilliant, but it's not too bad. Right, now let me put that onto the other grid. Aha! Now then, as you can see there, here's a funny business there. We've got a lower, where do you call it? We've got a lower output voltage. Instead of 23, we've got 22 volts RMS, and the distortion is 3.9. Right, so we're getting nearer now. So let me just swivel you back to the amp. So essentially what is driving the grids of those 2 output valves is a 6H8C at the moment, running at 8 milliamps cathode current each, 16 milliamps in total, and that's a cathode follower. Now then, these 2 big pots here, they control the grid voltage on those 2 cathode followers, and because a cathode follower, the cathode follows the grid, then if we change the grid voltage, we will change the voltage on our cathodes, and thus onto our output valve grids. So what could it be? At the moment, both of the cathode followers are getting their current from a constant current sink, or should I say they are sinking into constant current sinks, both of which is set, as I mentioned, at 8 milliamps. So what happens if we put a bit more current into the one cathode that is the problem, shall I say? So if I move all this out of your way. Let's have a look over there. I'll just zoom you in a tad. So we've got 22 volts. Let's see if altering the current makes any difference. I suspect actually it's the valve. I've already done this earlier, but I'm just doing it for you. No, that's making no difference. Right, that's not making a difference. So what I'm going to do, I'm going to try a different 6H8C. Power off and let that go down. Right, let me let it cool down a minute and I'll be back with the... Well, I've changed the cathode follower valve for one that, according to the information written on it, was pretty balanced emission wise. So the one I put in there had an emission test result of 9.4 and 9.8, you know, each triode, and then the one that I took out was pretty bloody balanced anyway. That one that I took out had an emission test results of 10 and 10.4, so both triodes are good. So why have we got that? Which is a bit peculiar. So what I'm going to do now, I'm going to go and have a look at just setting the DC conditions and see whether that does anything. Una momento, por favor, amigos. Right, I think I'm getting somewhere. So as you can see, I hope you can see, there you go, that has got better, and our output has gone up. So what did I do to change that? I didn't change the current. What I did change, spin you around a bit more, zoom you in, got the wrong way. So if you look at the meter on the right hand side, that's reading our grid voltage on our 2C34. So one is set to minus 16 volts, that's reading the positive voltage because I got my leads the wrong way round. So that's reading minus 23, and that seems to make it better. But that is biasing our valve a long way towards cut-off. So what I'm going to do, I'm just going to adjust the other valve for the same. As you can see, look, that's 16. So let's alter that one. That's right. With the dicky. Right, on the way. What was it? About 23, 24. Right. Yep. Right, so we've got 23.6 on one. And 23.4 on the other one. Right. Let me just give you back a bit more. Okie dokie. Let's have a look what that has done to our output. Ooh, that doesn't look good, does it? Well, you see, the problem with that is, look, we've got some crossover distortion, so that's no good. We can't do that, and we've still got this silliness. Right, okay. So that doesn't seem to be doing anything particularly apart from making things worse. Let me just adjust things back then. Where are we? We're adjusting this one. 17 volts, and as you can see, that's cleared up the crossover distortion, but now we've got a tip back. Well, just go and change the other one. Now then, I tested the two C34s there, and hold on, let me just concentrate what I'm doing. About 17, wasn't it? 17. Right, so that lowering the bias has made, you know, got rid of the crossover distortion, but we've got a tip back. But we've got more output. It was about 6 volts. Now we've got another, where are we, 7.7 volts. But the distortion is shite. I mean, 5% for an, yeah, that's not bad. And you see, the problem is, if I was to like increase the frequency 10 kilohertz. You see, now we've got some, looks like oscillation back. Let me just see if connecting the ground bus to chassis makes any difference. Ooh, we're back to this silly bitty business. That's me just grounding the bloody ground bus. I mean, what the... I really do not get this. Right, okay, that's made that worse. But you see what the problem is now. We're getting even worse distortion. The distortion has gone up to 5%. If I bung that to 20 kilohertz frequency, 20, it gets even worse. Got 5 volts, so our output's gone down, and the distortion's gone up to 8%. So, what else can we try? I'm sure I'm going to show what I'm going to do. I'm going to go into the other room and I'm going to show you the calculations that I did for what current we need to drive the grids of the two C34s. I'm going to show you that to show you that our cathode followers are correct, set correctly. And then the other thing I can try is to try different 2C34s, and I can also try swapping out the 6H8C for a 12BX7, which is basically an output valve in its own right. It's a bit fucking overkill for this situation. So first I'm going to try the 12BX7, which will mean altering the bias because it needs more negative bias to bias the valves, if you see what I mean, the output valves. And then if that don't work, I'm going to try changing the two C34s for these ones here, which are not 2C3, well they are, no they're not, they are CV18, which is basically a 2C34, but a bit different, but the same. By the way, these valves were used in Spitfires for the transmitter, so just a bit of information nugget there. Right, let's go and have a play. So yesterday, or previously, we saw that the grid, the input to one of the two C34s was distorted. Why could that be? It's time to get us heads around some theory. This is a graph for a 6H8C, a Russian 6SN7. Over here on the left hand side we have anode current or plate current. At the bottom here we have anode or plate voltage, and these are our control grid lines, let's call them. So to try and understand perhaps why we had a distortion, why we had distortion going in to the 2C34 grids, let's have a look at the DC conditions first. So all in all, right, a cathode follower is basically just an inverted common cathode gain stage. Instead of the resistive element instead of the resistive element being in the anode, it's in the cathode. We're not using the resistor here, we're using a constant current sink, but they perform basically the same sort of function. So first we need to know what is the total HT or voltage that the valve sees. Well, our voltage, our HT of the amplifier is about 216 volts, and then I've also got to add on minus 16 volts onto that. So in total, the valve sees across it from anode to cathode, it sees about 330 volts, which is denoted by this blue line here. So that's our total. If we are running a valve with a constant current sink source, then our load line isn't like that because it's not resistive, it's just constant. So say our valve was set at 8 milliamps. If we carry that over here and at 330 volts, you'll see that that corresponds to this grid line here, which is, let me just make sure, that's 12 volts here. So if our valve was biased, say, over here, then it's in cutoff and we'll get a distorted waveform. If you look at this other line here, 5 milliamps, you will see that that corresponds to a grid voltage of minus 14 volts. So the more current we put into a valve, then basically the cutoff of the grid voltage decreases with more current. I hope that makes sense. So I think that was what was wrong. Basically I had the valve set to higher current, and I've subsequently changed that. Now the reason I set it at this high current was in order to drive the two grids of the 2C34 output valves. Let's have a look at a valve and let me try and explain why we need loads of current to drive a valve. So over here we've got a pictorial representation of a triode. We've got our anode or plate, we've got a control grid, and we've got a cathode. If you look at the valve datasheet, it has values, capacitance between the various electrodes of the valve. So it has a value for the anode to control grid, and it has a value for the control grid to cathode. Any two bits of metal, any two conductors with an insulator will always have some capacitance. So in this case our anode plate is made up of a bit of metal. That's a bit loads of bits of metal wound round for a grid, and the cathode, well, let's just call it another bit of metal. So there is capacitance there. When we put a signal into this valve, into a triode, then the capacitance between all the various electrodes will add up to make a value of capacitance. And what happens is, at high frequencies, then that capacitance really starts to have an effect, and it will distort the output coming out of this valve. In the case of our 2C34, It's a little bit more complicated in that it's basically a twin triode with 2 anodes, 2 control grids, but only 1 cathode. When we're driving a valve in class A, B1, then normally the grid doesn't pull any current. It has a very high impedance to most signals, so it's not really a worry. However, you can get a situation where you start to overdrive the valve, grid current will flow, and instead of the current going from the cathode to the anode, say, or vice versa, what happens is current will start to flow in there and will start to flow into the cathode, cutting off that, and that's called blocking distortion. In the case of class AB2, then we expect there to be some current flowing into the control grid, so we need the driver that is driving this valve to be able to source that current, and also to have a very low output impedance so that it can drive it. To work out the total capacitance of a valve that the driver sees, this is the formula here. So what we need is a gain plus 1 times by the capacitance between the grid and the anode, plus the capacitance of the grid and the cathode, plus any stray capacitance. Normally in most sort of calculations we sort of call our stray capacitance about 3 picofarads, and in this case our gain is about 15, but this is pulled off the data sheet, and this was with the anode at 250 volts and the control grid at -7, so it could be more than this, so it's only a rough calculation. Our capacitance between the grid and the anode is 2.7, and between the grid and the cathode is 6 and 3. So let's work that out. What is that in total? There's a calculator. So what we got, 15 times by, just going to open some brackets there, and then we've got 2.7, let's just call that 3 plus 6 plus 3, there we go, and that gives us 180 picofarads. That gives us 180 picofarads total input capacitance. Impedance is just a frequency dependent resistance of any particular circuit. So normally a resistance doesn't change with frequency like in most circuits, but when we're driving it with an AC signal, then it depends on the frequency. So next, let me just write that down, 180 puff, 180 picofarads. Next we need to figure out what the total impedance is, and so to do that we use this formula, 1 divided by 2 times pi, which is 6.28, times by the frequency times by the capacitance. Right, let's bring that into the calculator. 1 divided by, open brackets, what we got, 6.28 times by the frequency. Now the highest frequency, let's just call the highest frequency that this amp will see is 20 kilohertz. 20, 1, 2, 3 zeros per kilohertz, times by the capacitance, but it's got to be in farads, so it's going to be a fraction of a farad. So a picofarad, oh god blimey, it's 1 picofarad is 0.00000000001. That's one, what's it, so loads of bleeding zeros. So we've got 0.000, so you can't fucking see. 0 0 0 0 0 0 1 8 0 close brackets, and that gives us an impedance of 44 kilo ohms ish. So let's write that down. Where are we? Equals 44 232. Cancel that. So that's the impedance of the valve of the grid. I hope that makes sense. I'm not a teacher, so I'm doing my best. I hope you're keeping up with me. So next, what current do we need to whack into that grid in class AB2 to get the valve to drive cleanly without distortion? So next we need to figure out what current we need our cathode follower to be able to shove into the control grid of our 2C34. Now I consulted the boffins on this, and they told me that the impedance, input impedance of the grid, is the capacitance times the frequency times the AC peak. Right, okay. Right, so let's just do it their way, right? So, where are we? The capacitance 0.00000. Oh fuck. Delete. Where are we? Let's go back. 00. I know you can do it with like to the power of whatnot, but I just know this way. 0.00180. 180 POF times by the frequency times by 20,000 times by the AC peak. The AC peak I pulled off the data sheet is 50 volts times by 50 equals, right, that is what current we need to shove into the valve. So that is basically 1.8, right, well, it's 180 microamps. So 180p there equals 180, oh no, sorry, yeah, that's right, UA. However, that's one way of working it out. We could just use Ohm's law, right, which is V over I R. Cancel. So our peak is 50 divided by 44k. 44232 equals, right, and that's giving me a different answer, 1.1 milliamps. So I set our constant current sinks for the cathode follower at 8 milliamps, which is a bit overkill. However, we're not done yet. If we look at our illustration here of a valve, essentially I have it connected like that. I've got the two grids connected. However, are those grids in series or in parallel? Well, they look like series looking into, you know, we've got a drive in current going into there. So you would think it'd be series, wouldn't you? Or is it in parallel? So let's work it out for each case. So the cathode follower looking into the valve either sees 180 picofarads or 360 picofarads. So let's do the sums again. 0.000, another 3 zeros, another 3 zeros, and 360 times by 20,000 times by 50 equals, right, well that gives us another answer, which is 360 microamps. So that would be if the capacitances were in series. 360p equals, right, okay, right, 360 microamps. If they were in parallel, they would be halved, because the capacitances are different to resistances in series or parallel. They're opposite, right? So it could be 90. Right, there we go again then. 2, 3, 4, 0.00 times 5 times 5. Right. And that gives us 900 micro 900 UA. Right. Now I would have thought, and I started out on the premise that we would need a lot more current than that. So that's why I set it for 8 milliamps, and it originally I had a 6 BX7 in there running at 15 milliamps, which is just fucking overkill. That is basically, if I use a 6 BX7 how I had it set up originally, then that is running at the same power as the output stage essentially. Lastly, I will just say this: to drive any output stage cleanly, it is a good idea to make sure that you, however way you're going to drive the valve, is to use as much current as you can. So I think like something like an ECC82 6SN7 is better at driving a valve than say an ECC83. There's a bit more to it than that, but that's essentially it. And that's Patrick Turner, who was a designer of valve amplifiers in Australia, he's sadly passed away. That's the lesson he taught me, and that's a lesson I learnt from the first valve amplifier that I built, which was a 120 watt 6EL34 amplifier. The video's on there somewhere. Okay, so at the moment what I've done, going back to our driver's stage, here's our light on because it's going a bit dark. Here's a load line for our 2C34. To draw a load line in class AB, then what you do, I'll just run over this briefly, but if you really want to learn about it, go onto the Valve Wizard website. This is a push-pull output stage. So in class A, essentially the two valves see half of the output transformer impedance, and so this pink line is that load line for class A. For class B, it sees a quarter of the load line, because in class AB the valve is cut off half of the time, and so there are two different whatnots here, but this is the one, this is the actual one, and this is the actual impedance of my output transformer that I wound way back. And as you can see, this is our maximum dissipation that we shouldn't go over if we don't want to kill the valve, and as you can see, that is way over. The other thing you do to get the class AB composite, because it's in class AB, it's in class A for only a little time, you know, just chugging over. It's not, I think I worked it out to about 800 milliwatts is class A, so it's not really very good in that respect. And so what we do, we move our class A load line up like so. Look at the Valve Wizard website, because I don't want to get too bogged down in theory. But if you see here, this is what I worked out as roughly where we need to bias the valve. Here's our minus 12 volt grid line, grid curve should I say, minus 18. So I worked out we need about minus 16 volts on the grids, and as far as I know from testing and all that, that's right. Oh, I did miss one thing going back to the earlier thing. One thing I didn't mention, apologies. So we've got 330 volts, which is our total value that the valve sees across it. Regarding our grid lines, from the DC conditions that I pulled off, testing and all that, then actually what these grid lines represent is not just the grid voltage in isolation. All this information here is in relation to the cathode. So our grids of our 6H8C are actually at minus 24 volts, which as you can see puts it right into cutoff, but that is not the actual voltage. The actual voltage is take away 10 volts, because the grid cathode voltage, DC conditions, is 10 volts separates them. Remember always that a cathode follower, the cathode follows the grid. Anyway, that's a little bit of theory. That's how to work out the impedance of a valve, and it's pertinent whether you're running it in fixed bias, cathode bias or whatever. A valve always has capacitance, and then there's another sort of thing to throw in the mix there, which is the Miller effect, but you need to look that one up for yourselves, because if I start rabbiting on about that, then we'll be here for fucking hours. Right, back to the amplifier. So what I've done, in light of all that information and calculations and all that, I've reset the constant current sink current that the cathode follower is running at. So instead of 8 milliamps, I've got it set to 5 milliamps. And that has cleared up the signal going into the grids. However, I still have a problem, and as I will hopefully show you, it isn't anything to do with the driver stages or anything like that. So we'll deal with that next, and then this will finish up the video hopefully. Well, this is insane. That is 100 kilohertz there. That is incredible. This is the output of our amplifier. Just turn you back there. Turn you back out again. Right, let's bang it to 1 kilohertz. Frequency 1 kilohertz. As you can see, it looks all cushy at the moment. And then last time when we went to 10 kilohertz, we started getting distortion. Let's bang it into 10 kilohertz. Frequency 10 kilohertz. And distortion is 2.6%. Looks good, doesn't it? None of that peakiness, none of the tit at the top. No high frequency nonsense. Right, frequency 20 kilohertz. Now normally we would see some attenuation of the signal by now. Yeah, in all the amps I've ever tested you do get a bit. We usually are about 3 dB down at this point, which is half the size of that. So let's just keep going up. I'm not going to go up in 10 kilohertz increments because it will just last all day. So right, frequency 40 kilohertz, and as you can see it's actually gone up. We've got a bit of boost there, so we've got a bit of high frequency peaking. 40 kilohertz, frequency 60 kilohertz. Getting, yeah, I think it's getting a bit, yeah, it is, I don't know. Anyway, it's still good, it's still got a strong signal. Frequency 100 kilohertz. Right, it's started to drop down, but that is really good high frequency response of an output transformer and amplifier. I mean, look at that distortion, less than 1% distortion. Yeah, that's pretty damn good. Right, let's find out what the crack is and what I think is wrong with the amp. I'm going to have to turn the amp off. One moment. So at the moment I've got the output transformer, instead of connected to my big dummy load, I've got this resistor here, which is a 10 ohm resistor in series with a 6 ohm resistor at the back, so we've got 16 ohms altogether. Right, so now let's bang it back on to our 8 ohm load. Switch on, make sure everything looks okay. That's a 20 kilohertz signal, 8 ohm dummy load, half of what we had before. As you can see, we've got some flattening and distortion. Distortion is 7%. Frequency 30 kilohertz. Frequency 30 kilohertz. Yeah, wrong. Just wrong, innit? Let's have a look. Distortion 6.8. I mean, negative feedback might clean that up, but I doubt it. It's nowhere near as good. And then if I bung it at 10 kilohertz, you see what I mean? At higher outputs, then we're starting to get, looks like somebody's taking a chunk out of it. So I think we'll cut this video there. I was going to play some music through it and everything, but I don't think there's any point because it's not properly set up at all at the moment. So what do all those tests mean and all the theory and all the rest of it? I'm pretty sure that the impedance ratio of the output transformer is wrong, which I suspected right from the start. However, like, winding the thing was like you know, quite an intensive thing to do anyway, and I've already done that twice, so it looks like I've got to do it again. I'm just going to run it past the boffins just to make absolutely certain, but I think that's what I've got to do, and then obviously I've got to wind the other transformer. However, that is like a, you know, that's really dodgy thing and everything, but it's the first output transformer I've ever wound, so I knew it would be a steep learning curve. As far as all the rest of it though, the layout and the circuitry and the DC conditions, the biasing of the various valves and whatnot is about right. Might need a little bit more tweaking, but shouldn't need much. Yeah, this has been a bit of a long one, this amp build. It's been very challenging, but that's how some amp builds go. The main thing is that I'm learning something. Anyway, it's getting really hot in this workshop again. The sun is shining full bore, and with that I'll bid you all adieu. Thank you very much for stopping by. Thank you all very much for watching. Take care of yourselves. Ta-ra for now.